Hello, and welcome back to 600. We're about to move away from probability, but before I do, I can't resist looking at a probability question that has stumped many supposedly clever people, the so-called Monty Hall problem. The problem is based on a television game show called Let's Make a Deal. The show was popular in the 1960s and 70s. Imagine that you're on that show, and you're given the choice of 3 doors, 1, 2, or 3. By the way, the people who were on the show dressed up in silly costumes in the hope it would attract the idea of the host, Monty Hall, who would invite them up front to play. Behind one of the doors is a car. Well, okay, maybe it wasn't this car in the 1960s. And behind the other 2 doors are goats. The contestant is asked to choose a door. After, let's assume you're the contestant, after you have chosen a door, the door remains closed. Monty Hall, who knows what is behind the door, now has to open one of the 2 remaining doors, and the door he opens must have a goat behind it. After Monty opens a door with a goat, he will ask you, the contestant, to decide whether you want to stay with your first choice, say door number 1, or switch to the last remaining door, in this case door number 2. What should you do? Well, the audience will shout all sorts of advice, but you should ignore it and figure it out yourself. The problem has been around for quite a time, and the literature suggests that most people get it wrong the first time. In 1991, Parade magazine published a correct solution to the problem, and approximately 10,000 readers wrote to claim that the magazine got it wrong. By the way, among those 10,000 readers, 1,000 claimed to have PhDs. I hope none of them were from MIT. If you were taking this class at MIT, you would now have the opportunity to play the game for fabulous prizes. Since you're not, you'll have to settle for my working the probabilities. I'm going to do that in 2 different ways. So let's look at the first way. Assume that without loss of generality, you choose door 1. Now, Monty will open another door. And again, let's assume without loss of generality, he opens 3. And there stands the goat. When the game started, it was equally likely that the car was behind door 1 or 2. Since we know it wasn't behind 3, it was placed at random, so 1 and 2 were equally likely. Therefore, it doesn't matter. You can switch or not switch, and the odds will be the same, 0.5. Sound plausible to you? It does to most people, but in fact, the argument is flawed. Let's look at the problem a different way. Again, you're the player and you make a choice. With the probability of 1 over 3, the choice is correct. That means that if you could choose the other doors, the probability of the car being behind doors 2 or 3, the remaining one, is 2/3. So with probability 1/3, you were correct, and the car is indeed behind the door you chose. But with probability 2/3, you were wrong, and the car was behind one of the other doors. Now comes the key moment. Monty opens a door that he knows does not contain the car. Note that this choice is not independent of the choice made by the player. The player has made a choice, say door 1, forcing Monty to choose 2 or 3. He does not want to open the door with the car because then the game would be over, so he opens the other door. So in fact, by switching, the contestant has a 2/3 probability of winning. It's tricky. When we work probabilities, we always have to think about whether or not we're looking at independent events or related events. To drive this point home, I want to look at some code that simulates the game. So here's the game. I'm going to simulate it for 100 trials. And I'm going to pass in this choose function. And we're going to look at 2 different ways that we might choose which door to open after the contestant has made a choice. We'll look at the number of times the contestant wins, the number of wins by not switching. We'll look at the number of times the contestant wins by switching, and the number of times the contestant doesn't win at all. The door will be behind 1, 2, or 3, and the guess will have to be 1, 2, or 3. So for t in range number trials, we first choose a place to put the car at random. The contestant then makes a guess at random. We then call the choose function, this one, which takes as an argument the guess and the door behind which the prize exists, because remember, Monty knows that, and it makes a choice. If too open is a prize door, then there's no win. Of course, if we play the game according to Monty Hall rules, this will never happen because he won't open the prize door. But we're going to explore the other option where he chooses at random. Otherwise, if the guess is the prize door, the contestant wins by sticking. Otherwise, by switching. And then we'll return the number of stick wins and the number of switch wins. Here are two possible choose functions. The first one is the one that is used on Let's Make a Deal. Essentially, Monty is just choosing the door that the contestant didn't choose and that has a goat. The other possibility is a random choice, where Monty will say, if the guess door is 1, we'll open either 2 or 3, so perhaps it might be the car, otherwise 1 or 3, else 1 or 2. Finally, we'll have a function that displays the results. I'm showing you this because it's using yet another PyLab plotting function, pylab.py, which produces a pie chart. Okay, let's go over to the code window and run it. So we'll first run it the way the game works, calling it with Monty choose, and we'll display it. Then we'll produce another figure in which we make the random choice, and we'll display it. Well, notice that if we play by the game rules, indeed it's the case that you double your odds by switching, shown by this pie chart. Of course, since there's randomness, it's not exactly 1/3, 2/3, but pretty close. On the other hand, if we play the game randomly, then in fact it doesn't matter, because an independent decision is being made, and indeed the odds are unchanged by switching.